Hi. So last time we saw that the number of ways to arrange n objects was that there'd be n choices for the first one, and then n minus 1 for the next, and n minus 2, and so on, so that the result was factorial of n. Okay, so we said number of ways to arrange n objects is n times n minus 1 times 2 times 1, which is just n factorial. Okay, so you probably wrote a function, I hope you did, called factorial that would take an integer n, and we could make it take a uint as well and return a uint. And a recursive way of writing this would be to say, well, if n is equal to 1, and remember our double equal since we're testing equality, if n is equal to 1, then the answer is just 1. So we're going to return 1. And that actually is going to be an int versus a uint, so I'm going to make this an int so we don't get tricky things with that being an n and that being a uint. So everything's going to be an n here. Else, if n is greater than 1, so n is equal to 1 is what we call our base case. So it's our simplest case at the bottom of the recursion. Otherwise, we want to take a piece off and say, well, we want to return n times factorial of n minus 1. So we have a small piece, n times whatever n minus 1 factorial is. And we've split it into a small piece and a simpler case of ourselves. Okay, so there's our function for factorial. What about if we want to say the number of ways to arrange k out of n objects? So say k is less than or equal to n. Okay, what might be the answer there? Well, we have n choices for the first object, and then we have n minus 1 for the second object, and so on. But this time, we actually only choose k objects, so we get down to n minus k plus 1. Okay, so there's only going to be k terms because we choose k objects. We're not choosing all n of them, we're just choosing k. And you can see that this is actually just n factorial divided by n minus k factorial. Okay, and if that's not clear, feel free to consult like Wikipedia or some online resources. This is called or permutations. Okay, so it's called a permutation of k out of n objects. And then the last thing, and I need to comment this, is that the number of ways to choose k of the n objects. So here the order doesn't matter. So it doesn't matter if we choose one object first or third. We can swap the first and the third elements and it's not going to matter. We're just worried about the group of the k objects. So the number of ways to choose this, and again, there's another thing that if you haven't seen this formula before, check out some online resources if you want to see the explanation for it. The number of ways to choose k out of n objects, or combinations, is, and now this is given by n factorial divided by n minus k factorial, let me do another parentheses, times k factorial. Okay, so n minus k factorial times k factorial is in the denominator, n factorial is in the numerator there. Okay, so this is the formula for a combination. Now, let's have a short exercise. Write functions, and let's call them perm of nk and comb of nk, computing these. Okay, so feel free to stop the video for a second and do an exercise by writing functions perm of nk and comb of nk to compute these two formula. And as a recollection, there's the formula for perm. So assuming you've done that, I can just show the answer. So the key part here is we're starting to see how subroutines can be really helpful. And we wouldn't want to reinvent the wheel and have to ignore the fact that we had our factorial function. So it's really helpful to use our factorial function. So I could write a function called perm of n k int. Okay, they both have the same type, so it's okay if I don't need to do n int k int, but I can do n k int. And let's say it returns an int, since it's the number of ways to arrange objects. And we could simply say, well, we said that it was n factorial over n minus k factorial, so why don't we just do return n factorial over, well, I'm getting a little too mathy. We need to actually do factorial of n divided by factorial of n minus k. Okay, and we know that this is going to be an integer because it's the number of arrangements of the object. So this actually looks like it might give us some weird integer division where it rounds off, but keep in mind that this value is going to be an integer to begin with. It's never going to be a decimal because it's the number of ways to arrange the objects. Okay, so that's a straightforward function for perm, and for com, we can use factorial again. So we could return factorial of n divided by factorial of n minus k times factorial of k. And we use the helper function that we've already written. Okay, you could get a little clever and say, actually, or just return the number of permutations. It gives us this much. And so you could do perm of nk divided by factorial of k. But you don't have to be that short about it. You're not only reducing that by kind of one expression. Okay, so there's our permutation and combination functions. And so this should be pretty straightforward. We're seeing how some functions are building on others. But the key question would be, are these good? Are they good functions? And I think the knee-jerk reaction would be to say, yes, they appear to, present the formulas that we want to give. So why don't, instead of hello playground, why don't we just plug in a sample value and make sure that it gives a value that we'd like to have? And the one that we could do would be, let's do combination of 1012. So this is a test value, and it's the number of ways to choose 2 objects out of 101 objects. So the order doesn't matter. We're just choosing a set of 2 objects. So we can compute this as, really, this should be 101 factorial divided by 99 factorial times 2 factorial. Let me parenthesize that appropriately because n is 101, k is 2. Okay, and the 101 factorial is going to have a 99 factorial in it. So it's 101 times 100 times 99 factorial divided by 99 factorial times 2 factorial, which is just 2. And you'll notice that this term and this term are going to cancel each other out. Okay, so we get a lot of cancellation. So it's just 101 times 100 divided by 2, and that's just 5,050. Okay, so we know, this is the mathematical formula for it. We can easily work this out by hand, essentially, and find that we know this is going to be 5,050. So here's a quick test, right? Anytime you write a function, we want to start testing it on values that we know the answer to. So let's print combination of 1012, and we get, where was I missing a return? Okay. If we get here, let's return -1. And what's good about that is that if we tried to give it factorial of -3, then we would get a weird value. Okay. Integer divide by 0. Okay, and now we actually see a runtime error. So this isn't a compiler error. It's not an issue with the grammar of our code. It's a runtime error where the compiler said everything looks okay. This looks like a completely reasonable function. And when the program was actually run, there was an issue that happened. And it's reporting back that the issue that happened was that we had a division by 0. Okay, so there's no way on the grammar level you could check this. But when you actually start running the program, you get a division by 0. Now what's strange about this is that if you look at the combination function, so it's factorial of n over this. That's the only division that happens. So it's telling us that a division by 0 is happening. And the question is, how in the world could we be dividing by 0 if we're dividing by what's apparently such a large number, okay, which is factorial of, well, in this case, not so big. It's just 99 factorial times 2 factorial. That's very strange. So this is a critical juncture in terms of when you start becoming a better programmer, is that many students get to this point, they feel like they've done everything right, and this looks completely reasonable, and then they don't know what to do next, and they kind of throw their hands up in the air. So what we want to get away from is doing that. We want to start debugging our code in kind of an intelligent way, and in a way that tries to diagnose things and almost treats, you know, errors that happen in code as like getting to the bottom of a mystery. And often I'd say that what you want to do is not plug other values into this. Well, you might start with that. You might say, okay, what about, you know, 104 combination with 5? And when we do this, we get an integer divided by 0 too. So it's not some weird extraneous case where I didn't, you know, give you a tricky specific example where if you took 101, the combination of 101, 2, or it's called 101 choose 2 because you're choosing 2 out of the 101 objects. That's not some single possible case that's causing an issue. And so students often are going to then look at the combination function and say, okay, well, let me look at the highest point. And actually in practice, what you want to do is when you start debugging functions, when you program from the top down, that's great. When you debug, you often want to debug from the bottom up. So you want to start at the lowest level. And so rather than plugging extra values of combinations in here, and I could try and print, you know, a smaller value that I might know, like 6, choose 3, something like that. And make sure that it's not messing up completely, and verify that that is indeed 20. So it's getting it right on some answers, but where I want to dig down to is factorial. Because if I can figure out, if I can say, well, factorial is definitely working, then I know it's something with the higher level function. So I want to start at the easiest functions, and if I can get them to where I'm pretty sure that they work, I can check them off and say, I know I don't need to look at those functions anymore. So let's start with factorial then. And let's try the individual factorials. So let's print factorial of, well, we can start at 2, factorial of 2, because that's calling factorial of 2, factorial of 99, and factorial of 101. And factorial of 2 is going to be fine. Let's try 99. And we get 0. Okay, so how in the world could we be getting 0 there? That's the tricky thing. Certainly 99 factorial isn't 0. So then we say, what could we do? And here's another point where we could kind of throw our hands up and say, I don't know. It's very easy to get completely flummoxed when you see something like this. But instead, let's say, what can we do? You know, we can only control the things we can control. And in this case, I know, you know, we're trying to get clues to the mystery, right? We know that factorial of 2 works, and we know that factorial of 99 doesn't work. So the natural thing that we would do would be, let's try the values of factorial between 2 and 99. Maybe somewhere along the way, things start to go haywire. And if I try 101, I can actually get another piece of information here, which is that factorial of 99 is 0, factorial of 100 is 0, factorial of 101 is 0. And if we look at how factorial is written, we start to get another clue here, which is that when you call factorial of 101, it returns 101 times factorial of 100. So if factorial of 100 is 0, factorial of 101 is definitely going to be 0, which means that factorial of 102 is going to be 0. And everything past that is going to be 0. So what we need to find is something's going on that's causing factorial of something to be 0. And then everything past that point is becoming 0. So now we started with no idea what was going on. And once we just started to try and get a little bit of extra information, we started to learn a little bit more, okay? So again, if we know that things are going okay at factorial of 2, let's just try a variety of values. So let's do, and I'm going to show a for loop here, or the go for loop syntax, and we'll come back to this, but for I colon equal to 1. So we're going to declare a variable I that's going to start at 1. Let's let range I up to 40. So I less than or equal to, this is going to be for I going from 1 to 40. And we increase I by 1 at each step. Okay, and we'll talk more about for loops in detail later. But I'm just writing a simple for loop that's going to print, let's say, factorial of I is, and let's do factorial of I, and let's see what happens. Or let's go up to 50, for example, and let's just notice the pattern. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 6 times 4 is 24, 24 times 5 is 120. Everything looks completely reasonable so far, but as you scroll down, the first sign of trouble is that you see a negative number. And the next sign of trouble that you might see is they go from negative to positive, and actually the numbers were getting bigger, bigger, bigger here, and then they stopped getting bigger. And so we can see there's definitely something going wrong, and now we remember what we learned before about overflow, which is that once numbers get too big, they just start wrapping around, going negative, and even if we'd used UNs, we would have had the exact same issue. They would have gone probably one term bigger, but then they start wrapping around and going negative, and eventually what happens is that we multiply 34 by factorial of 33, and because of how the overflow works, we actually hit the number 0. And once we hit 0, like we said before, well, factorial of 35 is just 35 times factorial of 34. So we get this chain of zeros. So something that seemed completely perplexing at first, which was that we were getting a combination that was equal to 0 when it seemed like we'd coded it correctly. We've now gotten completely to the bottom of the mystery and figured out exactly what's going on. So I guess the next task, and what I would leave as an exercise here, is to think through how it is that we could actually compute the combinations without getting this issue of overflow, because we should be able to go straight to the number 5050 without blowing up the factorials along the way. And that's what I would leave to you as an exercise. But I do want you to take away as the moral, so if there's a moral to the story of today, it's that always try different things when you run into a bug, and don't give up, okay? I would add to this, don't think for more than 15 to 20 minutes on one bug though, and this is another really good reason why sleep is helpful, as well as procrastination being hurtful. And then the last thing that we learned here is that we often program top down, but it can be very helpful to debug bottom up. And that's it for this lesson. I just wanted to provide a short lesson on debugging and to provide those general ideas for helping you out when you hit a snag in your code.